Hi, welcome back everybody. So I hope you enjoyed the first talk and the short break. So now for a little bit of relaxation, let's get going with compiler optimizations. Always fun, right? Well, maybe. Because Jago created a really nice pub quiz for us, as promised. And the good news is that Jago knows where he's talking about. He already shared lots of his Java related knowledge on multiple conferences in different countries, including conferences like JVOL, DevOps in Belgium, Java One, and also QCon. And he's also a very experienced developer, and with his quiz today, you can win a special prize. You can win a free talk or a workshop from OpenValue. So this can be provided for your team at a company meetup, or maybe you want to have a private talk. So that will be possible. You decide. The second prize is also very special. It's a full year of AWS free tier usage, sponsored by our partner Amazon. So now let's get started. First, a question to Jaco. Why did you pick such a kind of boring subject as compiler optimizations in the first place for a pop quiz?
Yeah, that's a good question, right? Actually, a lot of my job is figuring out where bottlenecks are in pieces of code. So, optimizing small chunks, usually they are a mess anyway, so that's easy to optimize. But once you have some clean code, well written code, it's really hard to define where the problems are. So, you need to dive in a little bit deeper into the ecosystem to figure out where the problems are. So compile optimizations are a way of fixing most of those problems, but you need to know where to look and well, how to uh, uh, how to use them. So normally these talks are heavily based on bytecode and even machine code and really dive in deeply. But that's not what I really wanted. I wanted to show some real use cases that well you could pick up today and maybe implement tomorrow in your code and write cleaner code or better code or at least better performant code or make the decision of why you choose something A over B.
That's all right, cool. Really curious to learn about the quiz. So I see that now currently 24 users are connected. You can use the link in the chat to visit the site or scan the QR code with your phone. And now, please give the word to you, Jaco. Take it away.
Yeah, thank you. So, welcome to the introduction. Like I said, this will be a high-level introduction of how the Java hotspot compiler works. And you might think the hotspot compilers, hotspot JDK, well, there's just only one, right? Wrong. The hotspot compiler is implemented in most JDKs. Not all of them, but at least the most used ones and the big ones have a hotspot compiler in them. Uh, for example, the Oracle JDK, because that's the hotspot JDK, but also Graal or Azure or Amazon has a JDK. So all those JDKs have a hotspot compiler in them to optimize the code that you're using. So this will be a high level and with some questions. Please visit myquiz.org and log in. The QR code will remain on the screen for a few slides, and then we dive into the questions. Please bear with me. I'm single-threaded, and I need to do a lot of context switching because YouTube is lagging behind around 7 to 10 seconds. So I need to synchronize while speaking and reading the questions. And that's also why I will be actually explaining the answers and then showing the results of the questions, because normally you want to see how everybody did and then comment on that. But when I'm discussing the answers, you guys will still be answering the questions. So that's really a struggle for me. So please bear with me. So normally we write code like this. Right? This is a simple string statics class with a string hello world, and well, it's quite easily. So what you've written will be compiled into bytecode. So for example, this method will result in something like this. This is the bytecode that is used by Java to run on every system. So this bytecode is machine agnostic. So any machine that runs Java can normally run this code. So what the Java runtime needs to do is interpret this bytecode into machine code. So this bytecode will look like something like this in machine code. And I promise this will be the last slide of machine code or bytecode. So what you see in machine code is a lot of jumping around, comparing stuff, and moving all kind of stuff through registries. This is the code that the hotspot compiler will actually optimize. So not going to dive into this because that will be boring. So a little bit of background. There is something called a tiered compilation. Maybe you've seen that. But the first tier is tier 0, and that's what most of the applications will run in, because that's the interpreter mode. That's the mode when the application is just started up and, well, just interprets your bytecode into machine code, and, well, that's about it. But when your code is running, it will go to a number of phases. It will first enter the first JIT, and the first JIT is also called the client compiler. Maybe you have seen those in the past, that your application would start up with an argument called --client, which signals the runtime that it would only use the client's hotspot compiler, because your code is running shortly. So there's no need to do big performance profiling and add a lot of counters to a lot of code, because those code will run only once or twice and then it's done. But the second JIT, or tier 4, is actually the server compiler. The server compiler will optimize code that's running a long time, or at least it's called a lot of times. So around a few thousand times, it will start to optimize your code. It can only do that when it knows it has run a few thousand times. So it needs some counters and profiling data. And that counters and profiling data is actually provided by the first JIT. But when your application is starting up, then you will see that the second JIT, or the server compiler, is actually quite busy, because a lot of code is spun up, a lot of code is executed, and all is fed to the second JIT. It's still figuring out what to optimize and what not. So when it's too busy, the first JIT will only add counters. So it won't envelop in everything to create a lot of profiling over a lot of code that will slow your application down. So it will only add simple counters for your piece of code. And based on that, it can make some decisions to either optimize it or not. And when the second JIT is actually a little bit freed up, it will actually start entering the profiling stage and adding profiling, and add it later to the server compiler. But there's also something called a trivial method, when the method is so simple that the client JIT can optimize it. It will actually handle it itself, and then it's done for. So that's the JIT compilation. And the question will actually sometimes go about the interpreter and the second JIT. So what are the difference in performance between the interpreter mode and the second JIT? So I'll leave out the small optimization that's done in the first JIT and focus on the second JIT, although some of the optimizations are done in the first JIT, but those optimizations are still valid in the second JIT. So how does this look like when your application is running? Well, if we graph it out over a number of iterations, first your code will run quite slowly in the interpreter mode, and then the first JIT will kick in, do some optimization, do some estimations, maybe optimize it wrong, do a lot of stuff, add a lot of profiling data, and then the second JIT will actually dramatically improve the performance of your pieces of code, and then it will run a lot faster. Although sometimes the second JIT makes a wrongful assertion. For example, that a field is always A or always B, and then it encounters that field will also be C. Well, you didn't expect that one, so it needs to de-optimize the piece of code, and then it will repeat back to the interpreter mode and actually the first JIT, but then it knows what it can expect. So the next iteration of the optimization will be a lot smarter and a lot better. it might not run as fast because it now needs to handle more branches, for example, but hey, at least it's running constantly. So doing performance testing in Java is quite annoying because you need to have reliable results. And for that, I've used the JMH. That's the Java benchmark harness, and that's really useful for benchmarking small pieces of code. So when we dive into an example of this, you'll see a piece of code with a lot of annotations. Well, it's just plumbing. You can, for example, say how much warm-up iterations it needs to do, how many iterations it actually needs to do the measurements, create some data, do some setting up. But actually, the most important part is in the box, and that's the benchmark method. For this case, it's a forward loop, and it always, or usually, takes a black hole with it, and a black hole is used to actually consume stuff because the hotspot compiler is uh, quite frank to optimize a lot of code. So if we do not use the black hole and have a loop that iterates over a big array, for example, and only does the get of a element and assign that to a string and does nothing with it, the hotspot compiler will actually see that and will see that string s is no longer used. The get is pointless, it has no side effects, so that can be removed as well. Then it will see it has a empty for loop. An empty for loop is completely pointless, so it can remove that as well. And then we are left with an empty method. Benchmarking empty method is, of course, quite pointless. So that's why we need to have a black hole that consumes, and that consumes something, and actually under the hood it does nothing with the thing that it consumes. But at least the hotspot compiler does not see that, and well, it thinks it's actually does something with string s, and therefore leaves the code alone because it's actually being used. So this is your uh, last time to visit the myquiz.org website and enter the code. I see that there are 25 people are actually in the quiz, so that's a nice group of people. So let's get started with the first question. And the first question involves a array of a class called strings, and it has a final integer number. And what is the most efficient way to do the concatenation of strings? Will A be efficient, or should you stringify the integer into a string of 10, or just make it easy for the compiler and do string 10 times in one string so it doesn't need to figure it out? Well, actually, all of these answers will result in the same bytecode. The fun thing is that the hotspot compiler will automatically optimize and concat any strings. So what it does is the string int of the integer number, it can, as it is final, it can encapsulate it into a string. So it does that on compile time. Then it's the same as B, but B is only adding 3 strings to a single string. Those 3 strings will never change after they've been compiled. So what the compiler actually does at compile time is create one string called do 10 times, and that's about it. So what I've heard in the past was that a piece of code was called many times, and somebody split up a string into multiple lines because it was better readable. Then somebody said, well, that's not really a good idea because the performance of that is worse. But as you can see, the performance doesn't matter because it will actually be that one string after it's been compiled. So it's completely pointless to have a big string 8,000 characters in. Just split it up into multiple lines and the compiler will handle this for you. And luckily, 28% of you guys also knew that, so that's kind of cool. So the second question. The second question will be a greet string, which does not have a final, and B has a final. Which one will be faster? Well, this should be easy. Well, actually, what happens here is quite funny. Because what you can see in A, the piece of code that does not have a final in it, will create at compile time a string builder. The string builder is used by the Java compiler to concat any strings. So that's normally that it will use that. But the compiler will clearly see that the greet variable was only used in the line below, never changed. So why didn't it optimize it? Well, a variable is a variable, and that can change according to the compiler. So that's not something the compiler will see. So A will actually create a new string builder, and B, as it is final, can be inlined into the string, and well, that will be just one string. So that's a lot faster. So what I've tried to do in every answer is write down the interpreter time and the time that it took the second JIT. So as you can see, option A is around, well, almost more than 10 times slower than option B. So that's really good to know.
There's a question, Jago, from Nick. Is effectively final. Isn't that the same?
It's almost the same, but it's as you can see, the compiler will not see that, and it will not optimize it the same way as it is a real final. So it should see it, but it doesn't see it, and it's still the case in JDK 15 because that's the last JDK that I've tested this on. So, well, it's still in there, and well, it could be improved. So next question, a string concat loop. Well, this is fun because I've seen this quite often in the real world. Whereas A is a string that's just a string that's concatenated into multiple iterations, or B, using a nice string builder and using that for a way to concat the result into a string. So I see that there is some slight thingy wrong with the quiz. It requested A, B, C, and D, while there was only A and B. And it said D was the correct answer, so that's my bad. But luckily nobody guessed that right, so everybody gets the same number of non-points. But the correct answer would be B, and luckily 54% of you guys did see that.
So there are a couple of questions coming in
Yeah.
also about the last question. So the final thing, is it only true for strings? That's effective what you told us.
It's not only true for strings, it's true for any variable that you decline. So if you created a variable integer or int, it will not inline that until it's final.
All right. And do you know how well other JTM languages like Kotlin exploit this?
I have no clue. So if anybody knows that, leave it down in the chat or leave it down in the comments.
Thanks.
So the string concat loop, well, as you can see, what happens in bytecode is that option A will create a string builder to concat the integer I to the result. So for every iteration, it will create a new string builder. And well, creating a new string builder is quite, well, not quite expensive, but it's a little bit of expensive because the garbage collector also needs to clear that thing up. Whilst option B, well, you have one string builder, and that one string builder is used throughout the loop, and no new classes have been created. So luckily, most of you guys knew that. unfortunately, something went wrong with the quiz here. So hopefully, I see what went wrong. It showed the wrong question, because the question was for about inlining. So let me give first an introduction into inlining. Inlining is when a method calls another method, and that method is called so many times that the compiler will see, hey, why not inline or include that piece of code that's in that method into the method that it's calling. That would optimize it a little bit, because it will then no longer need to do a method call. And as it's no longer doing a method call, it's a lot faster because it doesn't need to do any stack manipulation and that kind of stuff. So inlining is quite fun. So the question would be, how far can we take this? But that's the question that we already done. So that's really annoying. So this is the annoying bit of doing a live quiz and seeing what's going on. I guess somehow a question got removed from the quiz. I'm sorry about that. But I will give the answer to this one. The inlining, actually, you can take inlining quite far. Because in option C, you will see that it creates a new calculator class and then call the method sum on that. What actually the hotspot compiler will see is that the new calculator class is being created and then no longer is used, but also it doesn't have any side effects. It only is used there to function as a method wrapper or helper class for the sum method. It will actually remove out the entire instantiation of the new calculator. That way, it's just a method called sum, and that way you can inline the sum method. You can even take this a little bit further and have a real sum in that question, and that will also be inline, because that's just one nesting further. There is a limit to this, however. You can only inline 9 methods, so that's really not that much. If you're really going berserk in clean coding and use a lot of small methods, you probably will hit the limit of which methods can be inlined and which will not be inlined. Luckily, there's a compiler flag for that, and that's called max inline level, and you can set that, and that way the compiler knows what you actually want to do, and you can set it, for example, to 36 or so. Because that 9 was chosen, I believe, in JDK 1.3 or 1.2, at least a long time ago, when this optimization was introduced, and never changed after that, because, well, it will probably break backwards compatibility if somehow it does 8 or somehow does 20 inlining attempts. So you can tune this. Well, it's quite fun to tune around with this one if you're using a lot of small methods and using extreme clean coding. So, next question, and actually the question that's in the quiz right now. So you have a lot of time to read the question in the quiz. And that's about a toArray. Which is faster, string 0 or creating array with the size of the actual list? So what you will see is that the string 0 is a lot faster than with the size. Well, that's really odd. And the fun fact is that even Finebugs used to incline that it was faster to do the size method instead of the 0 one. So what's going on here? So if we go and look into the toArray function, that's actually using an array copy function underneath. It will see if the destination size, if it's 0 sized, it will do just a simple malloc function call. It will just allocate the memory that is necessary for the array, and then it's done with it. But when you pass it in an array that already has a size, it does not know what to do with it. It could be an array that's also already being used or not. It doesn't know that. So what it does is actually iterate over the entire array and will null out the entire array. So it needs to iterate over the entire thing. So that's a lot slower than just a malloc call and allocate some piece of memory that's probably available. So this is why giving it a size 0 is faster than the actual size of the array. So, next question, that's about boxing. In this case, we have for A, the primitive version, or B, the boxed version. Is the compiler able to actually optimize this piece of code? Can B be as fast as A when it's optimized? The answer is option A is a lot faster because it does not need to do any out-of-boxing. The compiler will not see that it's only being used for calculation and just that's a wrapper object. It will just leave it out as an integer class and will actually be boxed, and that boxing is pointless and takes a lot of time, around 10 nanoseconds per operation in this case. So that's quite big of overhead. So if you're doing calculations with integers or any primitive types, please do them with primitive types and not with the object type, because, well, as you can see, it's quite slow compared to the original one. So null checks. I heard a lot of times null check hurt performance. Don't use null pointers because blah blah blah. So that's is that the case? Is option A as fast as option B, or will B be faster than A with a null check? So this is something well you see a lot of times in code. And well, I actually saw that the question was not started at the correct time, but hey, you can't win them all. What you can actually see, what is happening underneath, is that when the second JIT kicks in, that you will see that the performance is around the same. In interpreter mode, the null check is a little bit slower. Well, that's what we can assume, because a null check, well, it does something, it's code, it needs to be executed, it needs to check something, so that needs to take a little time. So option B is, of course, faster in interpreter mode. But when the hotspot compiler gets a hold of it and actually optimize it in the second JIT, it will actually completely remove the null check if it's never encountered any nulls. That's the big caveat here. If the null check sometimes encounters a 0 and sometimes a non-zero or non-nil, then the check is valid and then the check needs to be executed every time. But if the check always ends up in the same state, that holds true for any Boolean check. So if the Boolean check always is the same, then it will be completely removed. And that also includes every piece of code and every thing with it. But you might say, but what will happen if string s becomes a null all of a sudden? Well, then it actually will run into a null pointer exception. And underneath that will be a segmentation fault at runtime. But Java will catch that segmentation fault and will see, hey, a null pointer is not something I expect here. My assumption that I removed a check for null was invalid. And then it will de-optimize your piece of code, and then we'll add in back the null check, and then it will know, hey, the null check is valid, and well, it needs to be actually be there because sometimes it is null and sometimes it's not null. So what you can see actually in the machine code that's being generated, well, the first piece of code has a little bit more bytes of machine code than the second piece, because, well, it's in the second piece it's missing out the null check. But when it's fully optimized, it's exactly the same number of bytes. Well, that's really cool. So next question, let's make it a simple one. And that's about math. If you do a lot of math, which one is faster? Java 8 or Java 9? And I know there is a fast math library in Java 8. So we're comparing here the stock math libraries from Java 8 to Java 9. Well, luckily, of course, Java 9 is a lot faster than Java 8 because they swapped around the math library under the hood. So that's why Java 9 is a lot faster. And as you can see, luckily, a lot of you guys knew that already. So that's cool. So for loops, which one is more efficient? The classic int for the classic loop, or a while loop? It's a bit of battle of the old for loops. I don't know who uses them on a regular basis. Well, you should use them if you want to index for something, but there are modern ways to do this. And fun thing is that is actually the same piece of code that you're looking at. B is the compiled version of A. A is nothing more than a compiler or a syntactic sugar. And I see that, well, almost everybody knew that, so that's kind of cool. So next way to write for loops. That's with a enhanced for loop, or use a iterator. But also here, it's exactly the same what we're looking at. Option B is the compiled version of option A. Option A is nothing more than syntactic sugar again. It just uses the iterator to iterate over your list, for example. And, well, this surprises me a little bit, but because it's called the advanced for loop, so well, it's only syntactic sugar. So, well, this is something to keep in mind. So an on for loop is not faster than an iterator because it's an iterator. So pitting those two together, the advanced for loop versus the old one in A. So option A is the old one, and option B is the enhanced for loop or the iterator. And option A is of course the same as a while loop. And this one yields a very interesting result. This is a result that I find quite interesting, because what you will actually see is that with B, that's a iterator, it will create actually a class, because you will get a iterator, and, well, that's a class and needs to clean that one up. But when it's iterating, it's well, a little bit faster. When it's fully optimized, well, then there is no point of using or choosing either of them, because they will compile out to roughly the same piece of code. So that's not what you want to optimize for. But when you have a lot of code that's running in interpreter mode, a enhanced for loop is faster than a old for loop.
So there's a
And why is that?
question slash remark, Jago.
Yeah.
Is it not based on the implementation of list?
For this question for B.
I guess, yeah.
Good question. I'm using a array list here. But I think it's of course the iteration speed of any type of list will differ. So I might forgot to tell this is a array list. Because of course you have a linked list and a lot of other types of lists, and those perform in different ways. So these results are valid for array lists. So good question, good remark. So what's going on in a array list then? What you will see is the list.size is actually called for every iteration. So, and it will actually do some nasty checks underneath as well, because if you look at the code that's being used, the size will actually check for code modification and that kind of stuff. So it needs to do a lot of kind of checks, and that way it will slow down a little bit. You could try to assign list.size to a variable, but somehow it won't be optimized as it would normally be. And that's probably because the optimization that are done are quite strict in what kind of syntax they expect. So if you move some pieces of code a little bit, then it won't be optimized at all. And I think that's the matter here, because it won't recognize it as a normal for loop. It won't do, for example, loop unrolling, which I don't go into to here at this time. But well, this is the way the normal for loop works. And you'll see a lot of method calls in there. And with the iterator, it is almost encapsulated into a single method. So there's no overhead in calling a lot of other methods to do manipulation of the array and that kind of stuff. And therefore, it's a little bit faster. And especially with big arrays, this holds true. For small arrays, the speed change is not that dramatic. So, and especially when fully optimized, it's gone as well. So please use whatever you feel inclined to. But there is another way to do loops, and that's the cool old new way of lambdas. So which lambda will be faster, or option C, actually use the old style of iteration. And option B is actually the method reference that we use. It's the same, or it calls the same method as option A. So this one is funny as well, because what you will see here is that the lambda is actually faster than the old style of iteration. That's kind of weird, isn't it? Well, it's not, because the for each function, or the for each lambda, is actually running inside of the array implementation and doesn't do any other method calls. So that way it can eliminate a lot of checks, a lot of concurrent checks, and well, ensure that it's running as fastly as possible. And option B, a method reference, it's faster when there are a lot of items in your list, but if there are a few, it doesn't really matter. And that's because a method reference should be assigned to a variable first and then used, but the compiler will optimize that out for you, so you don't have to write that piece of boilerplating. Actually, you can't really write that piece of boilerplating, but it's something that the compiler will do for you. So that's why for small lists that's a little bit slower because it needs to create that method reference first and then use it. Whereas the other Lambda is just created once and then actually being used a lot of times. So Lambdas with a for each loop in our array list are really quite fast. So that's quite cool. And again, luckily, I see that a lot of people already knew this, so that's cool. So to wrap it up, and actually go to the leaderboard, we see that DT has won this competition, and it was quite fast as well, in 2 minutes and 50 seconds. So Yogi was a little bit faster, but had some questions, or had less questions, right? So congratulations to DT. You can contact Roy and claim your prize. Details should be in your screen right now. So to wrap it up with a nice quote of Kurt Donald, we should forget about the small efficiencies, say about 97% of the time. Premature optimization is the root of all evil, yet we should not pass the opportunities in that critical 3%. So taking that a little bit liberally, is to say write clean code first and only optimize your code if you determine that there is a significant problem with your specific piece of code. So don't try to implement all kind of optimizations at first. Probably it won't have any effect at all. So are there any questions, Roy?
Well, we handled a couple of questions during the quiz, of course. I
Yeah.
don't see any questions at the moment. I must say, I kind of made fun of the subject, saying it was boring and stuff, but it was absolutely tons of fun. I mean, loads of gotchas and some really surprising answers. Um, so, yeah, a really great quiz, Jago, and uh, like you said, Diti, you can write me an email or contact me otherwise on Twitter or whatever. Roy@openvalue.nl is my email address. And we can talk about how to get you your prize. So if there are no questions, no, I don't think so. Then we're gonna conclude this meetup. I hoped we would finish before 9 and we managed. So well done with the timing as well. Thank you all very much. It was, I think, our best attended meetup as well, next to being the best subscribed meetup. So that was great. And we hope to see you at our next meetup, which will be in February. And of course, don't forget to like and subscribe our YouTube channel if you liked all this. And that's it for us tonight. And enjoy the rest of your evening. Thank you very much. Bye.
Bye.